estem en directe a tothom i benvingudes a aquesta activitat amb motiu del Dia Internacional de la Dona a la Ciència. Avui comptarem amb 4 convidades que són investigadores de l'Institut de Ciència de l'Espai i participaran en xerrades de 5 moments, ja sigui en català, castellà o en anglès, traduirem el que sigui necessari. I la nostra primera convidada és la María Kopsacheili.
Hola a todos, bienvenidos. Bueno, primero que nada, soy Jorge Rivera, responsable de comunicación, y bueno, es muy interesante para nosotros poder celebrar esta actividad que se celebra en todo el mundo, en una celebración de las Naciones Unidas, el Día Internacional de la Mujer y la Niña en Ciencia, que se celebrará el 11 de febrero, y es muy importante, ¿no?, hacer este tipo de eventos, y es interesante destacar que estos eventos se realizan en todo el mundo, especialmente en países como España. La comunidad astronómica española es muy activa, y digamos que de las comunidades astronómicas es de las que más actividades hacen alrededor del mundo alrededor de esta observación. Entonces, bueno, tenemos esta actividad hoy. Vamos a tener, como bien dijo Alba, 3 exponentes. La primera es María Kopsacheili, lo dije bien. Ella es originaria de Grecia y es una postdoc aquí en el ICE, y estudia remanentes de supernova. Y bueno, todo por María.
Gracias. Así que tengo que abrir la presentación.
Sí, desde...
Estamos en algún problema técnico. Saludar también a la gente que nos está viendo desde casa y en YouTube, en nuestro canal de YouTube. Y si tienen algunas preguntas durante las charlas, pues pueden ponerlas en el chat.
Buenos días. I'm María Kopsacheili, and I will tell you a few words about me and about how and why I became an astronomer. So I'm from Greece. I was born in Athens. I did my undergraduate and master studies in Athens. And then I moved to Crete, to this beautiful city, which is called Heraklion, to do my PhD. And now I'm here the last 5 months for my first postdoc. And actually, I'm very happy because living and working in Barcelona is something that I really wanted a lot. So, why I decided to become an astronomer? When I was a child with my family, okay, matter of sound or camera? Okay, fine. Okay, thanks. So yeah, with my family, we used to go on holidays to Evia. This is a Greek island here, and more specifically in a region here which is called Daphne. In Daphne, during the night there are not many lights, so you can see a very nice sky. And I have spent 23 summers there, and every single night I used to stay a few hours on the beach just looking at the sky. And when I was 7, 8 years old, I got very curious about the objects that I could see in the sky, you know, about what they could be, how far they are, and how they look like. So this is when I decided to become an astronomer, just out of curiosity. And I said that to my parents, and for some reason they took me very seriously. And they were very supportive with me. They also bought me a telescope. But yeah, I mean, as a 7-year-old kid, I couldn't realize that this is a science. So I didn't want to be a scientist. I just wanted to be an astronomer. And I would follow this path, whatever astronomy is. And since then, whatever I was doing was to this direction. I mean, my studies, etc. I never changed my mind. I never thought that I could do something else. And so, yeah. And during my undergraduate studies, I did an internship at the Observatory of Athens. There I met my first supervisor, who is now a collaborator and a very good friend. And he's working on supernova remnants, among other things. So this is how I entered this field. And as most of you know, supernova remnants are the remnants of a supernova explosion. I'm working on extragalactic supernova remnants, and I'm interested in an unbiased study of these objects. So what I have done in 3 lines is to calculate and correct samples of supernova remnants from incompleteness effects. I have introduced diagnostics for the optical identification of supernova remnants, and have developed some models for populations of supernova remnants. And during all these years, I have been in various observatories, obtaining images and spectra to analyze and to study. Also, it has happened to take some images just for fun. 2 years ago, after an observing run at the Observatory of Crete, I took this nebula, the planetary nebula, it's called Dumbbell, and I took it in various filters in order just to make a beautiful RGB image. And of course, I have done a lot of data reduction, a lot of coding, and I have used statistical methods and machine learning techniques. However, my research is not the only thing that I like in astronomy. Astronomy gives you the opportunity to travel a lot, to meet new people, actually have friends from many countries, from many continents. And I think this is its nicest side, I would say. Well, and of course, apart from astronomy, I like to do more things, and I believe that we should do more things than just science. So I like hiking. I love being and walking in nature. And I like the music. I play some accordion a little bit. Sometimes I like to sing. I like watching football. As I said before, I like traveling. And of course, what I like more is to spend time with friends and my family. So that was all. Thank you very much. It was very clear.
So, like you were like at least studying the school, have you ever like thought, oh, maybe I wouldn't be able to become a scientist or what?
Yeah, actually, yeah. I mean, well, to be honest, no. I never. I mean, I had this dream. It was more romantic, actually. You know, because I just, I will do science. Because I want to do astronomy. And to be honest, I never thought of that. I mean, I had this, and I was going like towards this, and yeah, it could be. I mean, we have done many discussions about that. It could be, but fortunately, it wasn't, because also I had the people around like support me my family, friends, also professors from the school. So yeah, fortunately, I never thought about that. Thanks for the question.
Any other question? Have you found any interest in working in subject, or are we
Yeah, I mean, in the sense of like science or the social part? Yeah, I mean, yeah, there are some differences. Yeah, I'm not sure. Well, no, there are some differences. It's both of them are, I mean, in both institutes, let's say, if I have to talk about the institute that I did my PhD in here, I mean, there is a lot of work that they do, a lot of work there, and many actions, many activities like that. I think here, because it's a bigger institute, there are more opportunities to do more activities. Yeah, of course there are differences, but both of them, I really like both of them. So yeah, thanks.
That's working with exoplanets and experience. So we will talk about her experience. When are you ready?
Oh, thank you. Doncs, moltes gràcies. Doncs moltes gràcies per ser aquí, tots vosaltres els que esteu connectats online. Com ha dit el meu company, soc la Clàudia Soriano i estic fent un doctorat aquí a l'Institut de Ciències de l'Espai. I en els propers 10 minuts us faré un breu resum sobre qui soc, com he arribat fins aquí, i us parlaré breument sobre els exoplanetes i us portaré fins als hot Júpiters, que són els exoplanetes que estic investigant. Doncs, primer de tot, dir-vos que jo sempre vaig tenir un interès molt gran per l'espai en general i sempre ho he tingut com molt clar des de ben petitona. Això em va portar a estudiar el grau de física aquí a la Universitat Autònoma de Barcelona. Llavors, durant la meva part d'aquesta més acadèmica vaig intentar implicar-me des del principi en activitats de recerca, perquè realment moltes vegades tenim la ciència molt idealitzada, perquè coneixem molt a la part de la divulgació, o hem sentit a parlar de la ciència des d'aquesta part més divulgativa, però realment no sabem què és la ciència fins que realment no estem tocant i no estem treballant amb ell. Llavors, ja des de la carrera em vaig intentar implicar fent algunes pràctiques, algunes estades, etc. I el meu primer contacte amb la ciència més pràctica va ser el grup de radiacions aquí a la Universitat Autònoma de Barcelona, en el qual vaig estar tractant dades meteorològiques al voltant de l'entorn de Magi i també vaig fer algunes calibracions atmosfèriques que s'utilitzarien després per al Cherenkov telescop. Més tard vaig fer les meves pràctiques curriculars aquí a l'Institut de Ciències de l'Espai amb la Mar Mezcua i vaig estar treballant sobre la possible detecció de forats negres supermassius en galàxies el·líptiques compactes. I llavors aquí vaig tenir una mica el dubte de si seguir estudiant l'espai des de la seva vessant més microscòpica, des de la física de partícules, o bé tirar més a la part macroscòpica, més l'astrofísica. I vaig fer, per treure'm aquest dubte, vaig fer el meu treball final de màster sobre el bosó de Higgs carregat a l'Institut de Física d'Altes Energies i això em va fer tirar més cap a la part d'astro. Vaig acabar el grau, vaig fer el màster en cosmologia, física de partícules i astrofísica a la UB, on vaig fer el treball de final de màster a l'Institut de Ciències del Cosmos sobre una galàxia compacta molt específica, que és aquesta d'aquí. I res, una vegada vaig acabar el màster, vaig començar aquí el doctorat des del l'octubre del 2021, on estic al grup Imagine, estudiant els camps magnètics dels exoplanetes. Llavors, començo una mica des de la base i aniré profunditzant fins als hot Júpiters, que són els exoplanetes que estic estudiant. Per qui no ho sàpigui, un exoplaneta és qualsevol planeta que es troba fora del sistema solar. La majoria es troben orbitant al voltant d'estrelles, però alguns es poden trobar lliures, que són els que es coneixen com planetes interestel·lars, que poden estar orbitant al voltant de la galàxia i no tenen per què estar correlacionats amb cap tipus d'estrella. Fins a dia d'avui hi ha 5.243 planetes confirmats i, clar, aquest gran número d'exoplanetes, arrel d'això, ha sorgit la necessitat de classificar-los segons algun criteri. Llavors, aquest criteri és el criteri de la massa. Tenim els exoplanetes més petitons, que són els de tipus terrestre, similars als de la Terra, els que són entre la Terra i Neptú, que serien les superterres. Després tenim els que són similars a Neptú i després tenim els més grans, els gegants gasosos, com per exemple Júpiter i Saturn. I els que a mi m'interessen més són aquests d'aquí, els gegants gasosos. Llavors, com hem dit, els gegants gasosos són en el sistema solar i trobem Júpiter, Saturn, però poden ser inclús més grans, tenen masses d'entre 50 vegades i 10.000 vegades la massa de la Terra, per tant, pesen molt, tenen molta matèria i estan caracteritzats per no tenir superfícies definides, perquè tenen aquesta estructura gasosa, que sí que poden tenir un nucli relativament més sòlid en comparació amb la resta de la part més externa, més atmosfèrica. Principalment estan fets d'heli i hidrogen, tot i que de vegades també poden haver altres espècies. Són planetes de formació ràpida, és a dir, que triguen relativament poc en formar-se. Relativament poc en formar-se vol dir milions d'anys, perquè clar, estem parlant a nivells astronòmics, per tant, és... Llavors, dintre dels planetes gasosos hi ha un grup concret que són aquests hot Júpiters o Júpiters ardents. Els Júpiters ardents és un subgrup al qual té la característica que estan molt a prop de la seva estrella. El fet que estiguin molt a prop de la seva estrella fa que tinguin temperatures molt elevades, que poden superar els 1.000 Kelvins i tenen períodes de translació al voltant de la seva estrella molt curts. Clar, el mitjà és d'uns 3 dies. Llavors, clar, reben molta energia de l'estrella i estan molt irradiats. Perquè us feu una idea, reben unes 10.000 vegades més energia de la seva estrella del que rep Júpiter del nostre Sol. Nosaltres en el sistema solar no tenim cap planeta que segueixi aquestes característiques, però n'hem pogut observar fora del sistema solar. Llavors, totes les característiques que hem anat veient es poden explicar fàcilment amb la ciència que coneixem, però hi ha una característica que no es pot explicar, que és el seu rang. Llavors, si us fixeu aquí, tenim cada puntet simbolitza un d'aquests hot Júpiters que s'ha detectat. En l'eix vertical tindríem, perdó, en l'eix horitzontal tindríem la temperatura i amb l'eix vertical el radi del planeta. Llavors, quina és la idea d'aquest gràfic? Doncs la línia vermella indica el radi esperat per cada temperatura si només es tingués en compte la radiació rebuda de la pròpia estrella. Però, com es pot veure, la majoria dels planetes estan per sobre d'aquesta línia. Això què vol dir? Vol dir que necessitem un altre recurs energètic que ens permeti inflar el planeta. És a dir, l'energia de l'estrella no és suficient, per tant, hem de buscar alguna altra cosa que ens doni aquesta energia extra per poder-lo inflar. I una de les suposicions, una de les idees més estudiades és el que es coneix com a dissipació òhmica. La dissipació òhmica, al final, el que diu és que, com que són planetes molt calents, la seva atmosfera està ionitzada, per tant, hi ha càrregues. Llavors, aquestes càrregues, quan es mouen a l'atmosfera, generen corrents i les corrents en moviment generen dissipació. I aquesta dissipació és energia que es pot utilitzar per inflar el planeta. És més o menys algo similar a quan tenim una bombeta. Ens apropem a la bombeta, notem aquesta escalfor. Si aquesta escalfor s'utilitzés per inflar el planeta, podríem potser obtenir radis més grans del que realment ens esperem. Llavors, estic treballant en dos projectes diferents. La idea d'aquest projecte és agafar blocs d'atmosfera d'aquests hot Júpiters i intentar veure quan es generen turbulències i quan es generen corrents elèctriques i veure si aquestes corrents elèctriques tenen prou dissipació com per inflar el hot Júpiter. Llavors, això és una de les branques de la recerca. I l'altra part, el que estem fent és, per un costat, fer simulacions de l'evolució d'aquests hot Júpiters en períodes molt llargs, al llarg de la seva vida, tenint en compte dos tipus de dissipacions diferents, una més atmosfèrica i l'altra més interna. Llavors, la idea és veure i estudiar aquests models i després comparar-los amb les dades observades per veure quin dels dos models quadra més i sota quines condicions obtindríem més un match entre els diferents models estudiats i les dades observades que coneixem gràcies a les observacions dels telescopis. I a part de la part d'investigar i fer ciència, etc., no només faig ciència, sinó que també m'agrada molt divulgar. Per tot aquell que estigui interessat en l'espai en general, dir-vos que hi ha un grup que es diu ICE a Barcelona, des del qual s'organitzen moltes activitats de l'espai en general, no només astrofísica, sinó temes més de missions, satèl·lits, etc. O sigui que feu una ullada perquè just aquest dissabte organitzem una activitat a Lleida, tant per nens com per adults, així que qui vulgui estar convidat. I també, si algú vol saber una mica més de tot el que estic fent, demà faig una xerrada al Centre Cívic de Vilaurània, així que esteu convidats. L'única cosa és que si algú vol venir, us haureu d'apuntar. I, a part de ciència com a tal, m'agrada molt llegir, m'agrada molt mirar sèries, m'agrada molt sortir amb amics, cuinar, fer excursions i potser una activitat, un hobby no tan conegut o no tan típic, que és que faig arbres genealògics. Sí, tinc l'arbre genealògic de la meva família, té milers de persones, inclús hem arribat al 1.500, o sigui, he investigat bastant. I res, bàsicament això és tot. Merci.
Okay, I'll share your screen. Okay. Let's click through this.
So now we are going with the numbers. She's a PhD student at the institute.
Okay.
From the United States. Go ahead.
Great. Hi, everyone. Sorry. Okay, great. Okay. Hi, everyone. I'm Dane. I think I have met most of you. I see a lot of very familiar faces in the room, but for those of you who have never talked to me before, I'm from California. So I am from right about here. It's an hour south of San Francisco, which fits right there, which is right in the heart of Silicon Valley. So if you don't know Silicon Valley, it's where there's just a lot of tech companies. I kind of grew up around people who had parents who worked in tech, and I also had a bunch of friends whose greatest dream was to become like a head engineer at Google or something. And so I kind of grew up in this place where computers kind of were a huge deal. I never really even thought about physics until about the end of high school when I was. Okay. Yeah, I walk around a lot. Okay. Right. Okay. So I started thinking about physics in high school when I first met my high school physics teacher. I was about 16, 17 years old. And he, like many other teachers in my school, also had a side job in tech. So he was, I don't know, writing some weird app with the computer science teacher, talking about, I don't know, maybe improving the lives of teachers somehow. And so it was nice to see kind of a mixture between the things that I know, which is computer science, and things that I was maybe interested in, which was physics. I also grew up here. So I spent my years in school in San Jose, in the city, but in the summertime, my mom and I worked at a campground that she owned. And so for the summertime, I was as far away from computers as I possibly could be. And instead, all I had to do was work during the day and sit and look up at the sky at night. And so very naturally, I became an astronomer, became very interested in astronomy with, kind of a side interest in computer science. So when I decided to go to, when I decided to go to undergrad, I decided that astrophysics was the best choice for me. So that's what I majored in. And then I also did a major in computer science. So the secondary major I thought was just going to be kind of a side interest, maybe like a hobby. And then I started talking to actual physicists, and they were like, oh my God, you can code. Please work for us. And so this is kind of what my life has been. It's been kind of this weird mixture of the two parts of my life that have been so separate for the longest time. And now they are kind of, meshing together in this lovely way. So I did my undergrad. I did a couple of projects there that I'm going to talk about maybe a little bit later. And then I did my master's, yikes, all the way in Indiana in the Midwest, maybe about 3 hours away from Chicago, if that helps. I know this is kind of like a weird floating map, so it's kind of hard to see, but it's all the way, on the other side of the country. And so I did my master's there, and I did a couple of projects there as well. And now I'm even further east. So I think I'm just going to keep on going east. If anybody has any opportunities in Asia, that would be great for my postdoc. Okay, so this is kind of what my path was. And so what did I actually do during that time? So in my undergrad, I studied dark matter, specifically self-interacting dark matter, and what the cross-section of that could be using various probes. During the summertime, I had to make money, and so I worked at software engineering companies. I also interned at places like NASA and CERN, just as pretty much a computer consultant. And then in my master's thesis, I did simulation for cosmology, n-body simulations of globular clusters, and probing dark matter things. Great. And so now I'm doing my PhD in cosmology. I'm here at ICE and also at E5, doing kind of a mixture of high redshift stuff and low redshift stuff, but working with weak lensing and supernovae probes of cosmology. So I'm just going to quickly go over what cosmology is in case for some reason astronomers don't know what cosmology is. I studied the cosmological standard model, or lambda CDM, which is, I mean, everyone uses this. It uses kind of a basic model of dark matter called cold dark matter. And it's kind of ruled by 6 parameters. And it's kind of an explanation of the entirety of the universe, how it started, how it's evolving, where it's going to go. And so it's kind of incredible that it's only 6 parameters. The 4 that I care about, I know there's only 4 up here. I don't really care about the other 2. The 4 that I care about are these. So the Hubble constant, which dictates how quickly the universe is expanding. Baryon density and cold dark matter density, which is basically just how much matter there is in the universe and how much it makes up the energy budget in our universe. And then finally, sigma H, which is the fluctuation density. So I have this image of the PMB here. So you'll see the kind of the bright red bits here are where there's high density fluctuations. And so what I care about is the amplitude of those fluctuations in the early universe, because this is important for cosmology. Great, and the reason why I care about these 4 in specific is because we don't really agree on how they're measured or what they actually are. A nice image here on the, on the other side over here, is that of the S8 tension, which is a mixture of the sigma 8 fluctuation density and these 2 baryon and CDM density parameters. You can kind of see, maybe I'll move this a little. Yeah, you can kind of see that we don't really agree completely on what the value of this S8 parameter is. There's also a tension with the Hubble constant. It's called the Hubble tension. And it's a little bit bigger. There isn't really a great image for it, but there is a disagreement for what the Hubble constant is as well. So how do I actually probe these things? The first thing that I do is weak gravitational lensing. I do this pretty much majorly at E5 with the dark energy survey, basically measuring the amount of gravitational lensing that we see in the sky from galaxies, and from that inferring how much dark matter there is in the sky and how much luminous matter, how much matter in general is up in the sky. Because of the nature of these kind of studies, we're going kind of really far up into the sky, so mid to high redshifts, very old light that we're studying. This is an image of strong lensing, but it kind of gets the idea across. You have, light that's being bent from the matter that's in front of it. And so you get these kind of, sorry, I'm going to walk away from this for a second. You get these kind of arcs. This is an example of strong lensing. Weak lensing is a lot more subtle, and you can't really see it in an image. And so what we do is we study a whole bunch of data, and using the statistics in that data, we determine the matter that's bending this light. Great. So that's the weak gravitational lensing bit that I do. I also kind of study supernovae with the ICE group here, generally using supernovae peculiar velocities, or velocities that are kind of not with the Hubble flow, to study how much dark matter there is in our local cluster, just kind of reconstructing the matter structure close to us. And since it's close to us, that means low redshifts. And so I kind of study a large range of redshifts to kind of hopefully find some sort of fix for these tensions in the cosmological model. Great, so what exactly is it that I do? So I mentioned that I'm more of a computer person than a science person, or I'm kind of a mixture of both. So a lot of these are very computational heavy. So I study the effect of Z-blunders. So if you look up in the sky, the more we look up in the sky, the more galaxies we can see. The more galaxies there are in the sky, the more likely it is that they're going to overlap with each other. And so we need to find a way to de-blend those images so that they're 2 separate galaxy images. So I study the effect of these de-blenders on weak lensing surveys and our measurements. I also determine redshift bins for galaxies. So basically determining how far away these galaxies are from us so that we can figure out where the mass is. If the galaxy is being bent, we can figure out how far away it is and so where the mass is given that. I also make cosmological measurements using special galaxies. So we have a new galaxy sample that is really high redshift, so really far into the sky. So we measure both galaxy-galaxy lensing, so how galaxies' lights get warped, but we also measure how the CMB itself gets warped. Great, so that's kind of what I'm doing with the dark energy survey. And then here at ICE, I'm working with the host flows team in supernovae. Right now, I'm just kind of working on some, software projects. So working on a pipeline for reducing data that these lovely ladies are currently working with, and also giving talks on software engineering approaches. So doing code reviews and also talking about best practices for software engineering and cool things that you can do with code that most scientists aren't really aware of. Great, so I think that is the end of my presentation, but thank you.
Thanks for the nice talk. So, if you could have this both background in tech and astrophysics, I was wondering if you could see any difference in, for example, equity or gender balance in the two environments, or no? Thanks.
Really great question. The answer is yes. So I think tech and engineering in general are very different from science, right? And so tech, a lot of the time people are in it kind of for money, and it's very, very male dominated. I mean, don't get me wrong, science is also pretty male dominated, but in tech, it's kind of horrifying. I, went to classes where I was the only girl in the lecture hall, 150. And so I think a large reason why I'm not a software engineer is probably because of that. I think I kind of gravitated towards science and astrophysics in general because it's a more welcoming. Not to say that it's the most welcoming thing on the planet, because physics is also kind of notoriously horrible for women as well. But I think comparatively, I think science is a lot, I'm not going to say better, but easier for women. Yeah.
I don't know here for the
I would say yes. I think, again, growing up in the Silicon Valley, I learned to idolize a lot of people like, Elon Musk. And so, yeah, I'm saying that into a group of astronomers, of course, everyone maybe doesn't like him because of Starlink and because of a whole bunch of other things. And so, I mean, obviously, the more you learn, the more you realize that your idols might not be the best, So that's why we, grow. That's all I have to say on that.
I'm not sure about what you say. So you said that the models? Yeah. Yeah, sure. I mean, when you start, you don't know, you have no idea. And you realize, like, every year, I think, it's something every year, even every month. So, yeah, for sure. Just saying.
Then and what right now.
No, I mean, what do you mean? So, yeah, I mean, what I want to say is that when you start, you don't know how the people, you know how the people can be, how they behave. So then you meet people, you see that they love what you love too, and then you see there are people that support you. There are others that okay. I think as women we see this sometimes this trend, you know, that some are not very supportive, and yeah, I mean, yeah. Yeah, I cannot say something like very specific, but it's always different.
Well, so thanks for your talks. I would suggest you get in touch with girls. And actually, I'm going on Friday with a talk to my high school, because that's where the real problem is. Girls at 11 or 12, they really think that science is not for them. And actually, it's very much on the idea of the role model. I mean, if they see other women doing science and we try to get in touch with them, I mean, it really impacts. It doesn't seem so, but I already had this experience 2 years ago. And I actually, I was very much impressed of how my short talk and my short getting in touch with them made an effect. Actually, I will start my talk with this picture of the soccer team of the Barcelona. I mean, and they probably even remember when they were 5 years old, they were told that soccer was a sport for boys. And now soccer is so popular among girls. I mean, women always know. So is this a role model that we believe that it's not so important, but it is important. And I will suggest you get in touch with, well, maybe next year, there is this initiative of the Fundació de la Recerca Catalana. Actually, this Friday is going to be like 500 talks in different schools. And really, I mean, I can tell you a little bit more later on, but this has an impact. Okay? Only that, well, maybe you cannot explain so much sophisticated things as you have done today. It's obviously very complicated for girls. But this thing that other girls can do it really has an impact.
Anyone else wants to add something to the discussion? No?
So we can begin here.
Let's give another round of applause to the speakers, but also to our people that have been working in the institute.